Hey guys, my name is Kylie Ying and this is my machine learning course. If you've been following up to now, we've covered the basics of probability as well as statistics. And in today's lesson, we're going to dive deeper into an area that's adjacent to those two topics. We'll talk about continuous variables, distributions to represent those, as well as a special distribution known as the normal distribution. A random variable is just something where we actually don't know the outcome. Essentially, it's a variable, but the outcome is uncertain. And what do I mean by that? Okay, for a dice, let's say that we represent the outcome with X. Okay, so this represents the outcome of rolling a dice. Well, every single time we roll the dice, that number is going to change, and it's going to randomly change. We can't tell before we roll the dice, and the dice is random. So this here, this X is our random variable. And X can take on different values, right? So X in our example, this little backwards E thing means is in. It's like this is the set. So, which means that X has to belong to one of these numbers. So this E, this backwards E here means is in. So like X is in and then this set of numbers. So that means X can only take on these numbers. It means any value of X has to be within the numbers that I write. So 1, 2, 3, 4, 5, 6. And now every single time we roll the dice, when we talk about probability, we're actually saying, okay, the probability that X equals 1, well, that means the probability of rolling the dice X and seeing what that outcome is. What is the probability that that outcome equals 1? So this is going to be equal to 1/6. And actually, if we replace this with 2, that would also be 1/6. 3, that would also be 1/6, and so on. You know, assuming it's a fair dice. By the way, there's so much more to probability and statistics than what I can cover in this single lesson. And if you guys are interested in diving deeper, I highly recommend checking out today's sponsor, Brilliant. Brilliant is where you can learn by doing, with thousands of interactive lessons in math, computer science, data analysis, and AI. In Brilliant's lessons, you'll actually find hands-on problem solving that'll let you play around with concepts rather than just memorizing. And because you're not just memorizing, Brilliant helps you improve your critical thinking skills because you actually have to think for yourself when you're learning these concepts. And Brilliant's lessons are designed to be digestible little pieces that you can do a little bit of every single day. And so you're building knowledge day by day. Brilliant has a bunch of really great courses in data processing, programming, and AI. They just launched a ton of new content in data, and it's perfect for learners of any level, whether you're just starting out or whether you're trying to refine skills that you already have. In these lessons, you'll learn how to parse and interpret massive data sets, which is super applicable to this world of just growing data. And what's really cool is that Brilliant's projects allow you to work with real-world data sets, such as those from X/Twitter, Spotify, Starbucks, and more. The best part about all of this is you can actually try everything that Brilliant has to offer completely free for 30 days. Visit brilliant.org/Kylie Ying or click the link in the description below. And if you like it and decide to stay, you'll get 20% off a premium annual subscription. And so what we can actually do is we can plot these distributions. So for a discrete, so this in here, X can take on only discrete values, which means that they are set values that we've predetermined ahead of time. We can't get like 1.5. We can't get all the values in between 1 and 2. A non-discrete variable, so a continuous variable, would be something like height, right? Because literally you could be 162.478 centimeters. Whereas discrete is more like buckets. Okay, you can only get 1, you can get 2, but you can't get 1.5. And so for a discrete random variable, we can actually plot something called a probability mass function. So this is a PMF for short. And what this is, it's on this number line Well, let's say that, 1 is here, 2, 3, 4, 5, 6. So make these lines. And here we actually have axes. And so this is going to be the probability P. Well, we know that each of these is 1/6. So 1/6 is here. So actually each of these just have a height of 1/6. Okay, not too interesting because we're starting with an easy distribution. And now there's also something called the cumulative mass function. It's taking this, let's duplicate that and put it down here. So cumulative mass function, instead, we're actually going to be summing all these values. We want to know what is the probability that it's going to equal that number or less. So for 1, the probability it's less than or equal to 1, like the outcome of the dice, well, that is actually still 1/6. And then for 2, well, that's now 2/6, right? Because it can be 2 or 1. For 3, it's going to be 3/6 or 1/2 because, now we have 3, 2, and 1. Sorry, imagine that these are connected. Not very good at art. 4, 5, and 6. So eventually for 6, that's going to be 1 because the probability that 6 or less for a 6-sided dice is going to be 1. You might think that the cumulative plot is not that interesting, but what this helps us do is take a step back and look at the bigger picture. So like in real life scenarios, what we care about is we actually care about how probabilistic it is for something up until a certain threshold is met. And so that's what the cumulative mass function can tell us. It's what is that cumulative probability until some number. Okay, we've looked at discrete data sets, but now what about a continuous data set? Let's go back to our example of heights. And specifically, I'm actually going to talk about women's heights. What we can do when we have, a big enough sample is we can actually plot them on something, and we can kind of do the same, like what is the probability of certain things. So, we might collect our data and stuff might look like, people's heights are coming in, they're coming in a little bit all over the place. Well, these start adding up here. And this is it is a continuous data set, but we're just kind of plotting, okay, where are these values coming in? And so I'm plotting them kind of in 2D for a reason. So the data set might start looking something like this in our sample, right? And the mean in this case would be somewhere right in the middle. It would be representative of kind of, what is normal, the middle of this distribution. This plot that I've actually drawn here, this can be interpreted as also that similar sort of probability distribution. So this here, this red is a probability density function. And it's the same concept as this probability mass function, but instead of discrete values, we are actually saying, okay, on this continuous axis, what is the probability at a given point that, this person's height might be this number? And this can also be, turned into the cumulative function, because this cumulative function might look something like that. And this is basically telling us, let's say, that's some really tall height. Well, if this is 1 over here, then this number here, let's pretend that's like 0.943. Then essentially what this is telling us is that the probability that a woman who's representative of our sample, the probability that a woman's height is less than or equal to X this x here, sorry, let me use a different variable name because we've already used x a few times. So I'm just going to say m. So some height m, that just represents a number. The probability that a woman's height is less than or equal to m, well, that is actually this cumulative number here. So that equals 0.943, which is also 94.3%. So again, this is now the cumulative density function. Because we're plotting cumulatively, if it's, you know, this value or below, what is the probability of that? And that is what each point along this line represents. So a different example, you know, this one here, this might be 0.17. So let's use n, or let's not use n. Let's use L, some height L. Then the probability that the person's height, that a woman's height is less than L, is actually equal to 0.17, so that's 17%. Okay, so the cumulative is measuring up to a certain threshold. Like, what is the probability that, you know, this entire population fits under that threshold? Going back to this data set up here of the women's heights, you guys didn't, I mean, hopefully really question that I drew most of the points in the middle. And why? Because that's actually representative of our population. If you look at women's heights, most people are kind of in the middle, right? Most people have very similar heights, but of course there's gonna be some people who are shorter and some people who are taller. And those we call the tails because, well, they're kind of at the ends. And the occurrence of people who are shorter or taller than kind of generally everybody in the middle, well, that doesn't happen too often. So probabilistically, it's a bit lower. Exactly like how I drew this curve here. And that's something that represents a normal distribution. So let's talk about normal distributions a little bit. So a normal distribution is, it looks like this. This is the probability density function. And it kind of has a bell curve shape to it. So if you've ever heard of the bell curve, then that represents the normal distribution. Okay. And actually the first thing we're going to talk about is the standard normal function. So in the standard normal distribution. In the standard normal distribution, our x-axis is actually going to be in terms of standard deviations. So remember that standard deviation up here, we were talking about it. Remember that standard deviation is a representation of how far the data is away from the mean. And so something, you know, over here is going to be a higher standard deviation away from the data set than something really close to the middle. So here, this is in terms of standard deviation or sigma. And in a normal distribution, the mean, median, and mode are actually all at the middle. So this here, this is mu, the mean. But it's also the median, and it's also the mode. And we basically have these buckets of standard deviations. And here, don't let that confuse you. So this is actually the middle of the distribution. And in the standard normal, mu is going to be equal to 0. Because the x-axis is a standard deviation, and the mean, I mean, it has a standard deviation of 0. So this is our mean. And now something that's really cool about the standard distribution is that if we look at the number of standard deviations away from the mean that we are, plus minus 1, so that's here to around here, the empirical rule says that 68% falls in between one standard deviation of the mean. So plus minus 1 sigma, so plus minus 1 standard deviation, is actually 68% of the data. And now between plus minus 2 standard deviations, so that's this part here, in this purple, which also includes, of course, the 1 because it's a wider range, this is actually going to be around 95% of the data. Finally, between plus minus -3 and +3 standard deviations away from the middle, so that is literally almost the whole curve, that's actually 99.7% of the data. So 99.7% of data typically lies in between the -3 standard deviation mark and the +3 standard deviation mark. So you can see how if we have a sample that follows this curve, we have the function for finding the standard deviation. Suddenly we can say, oh, 95% of the population likely falls in between mu minus 2 standard deviations and mu plus 2 standard deviations, which is a really powerful tool. And so this rule is really handy because it gives us a quick way to understand how spread out our data is in a normal distribution without having to do that much fancy math. And so just in case you guys are interested in the probability density formula for a normal distribution, it equals 1 over sigma, so the standard deviation, times 2 pi, and then the exponential function, so e, that natural number e, to the exponent of x minus mu squared over 2 sigma squared. So this is kind of all the exponent of e. So let me make that really small to make it kind of obvious. So yeah, that's e to this power. And the curve that you see here, this one that we've drawn out, it actually, you can figure out the exact values at each point by plugging it into this function. And specifically for the standard normal, mu is equal to 1 and mu is equal to 0 and sigma is equal to 1. But it's not difficult to translate this into an actual data set, because what you can do is you can replace mu with the number that actually is representative of your data set, and sigma, maybe that's 10 or something. And now all of a sudden you have a normal distribution and it just scaled to your data set. And so the normal distribution is really powerful because it gives us a representation, a mathematical representation of a lot of phenomena that happens in the real world. And now all of a sudden we can plot things such as heights of a certain population, or test scores, or certain other things in finance or nature, biology, medical, science, etc. All these different fields. So finally, I wanted to go over 2 probability concepts that will also help you in statistics. So the first is the law of large numbers. Basically what the law of large numbers says is that the more samples that you have, and these samples have to be independent, meaning that one sample cannot influence the other sample. Then the average of all of these samples will actually be more reflective of the true average, the true mean, if it exists. So more samples you have, x bar, the mean, will become closer to mu, the true population mean. So that's kind of the law of large numbers. And then we have something called the Central Limit Theorem. The Central Limit Theorem says that the distribution of sample means actually approximates a normal distribution as the sample size gets larger, regardless of the population's distribution. So basically, if I have a bag of marbles, and this bag of marbles could be any distribution of red and black marbles. And what I'm going to do is I'm going to sample from the marbles. I'm going to collect a big batch of them, and then I'm going to count how many the percentage of red marbles in the bag. If I repeat that many times, so this here is the percentage of red marbles that I pick in my samples are actually going to maybe approximate a distribution that looks pretty familiar. Okay, so this is actually what the Central Limit theorem says, it doesn't matter what my population looks like. Every time I draw a sample and I calculate some value from that sample, if I collect this sample over and over again, that will actually tend towards the normal distribution. And the reason why this is cool is because the normal distribution, again, we've already studied it a lot. It's a handy tool that we know in statistics. So we can make predictions and draw conclusions about the data fairly easily without, knowing much about the original population. With this, I will leave you with a very basic understanding of probability and statistics, and hopefully, enough of a foundation that you can begin machine learning.